All right, so we're continuing our derivation of the T character table, and we figured out in part one of this series that we had 12 different symmetry operations, and that these fell into four different classes. We had an identity class, we had a class consisting of four 120-degree rotations, four C3s, a class that consisted of four 240-degree rotations, we call it four C3 twice, and then we also had the three C3 twos. So our first character table rule tells us that because we have four classes and character tables are always squares, we must therefore have four vectors or four irreducible representations. The number of irreducible representations is equal to the number of classes. And so we don't know the elements or characters in these classes yet. That's what we're going to figure out in this video. But we do know that there's four of them, four vectors, four irreducible representations. So I'm going to call those gamma 1, 2, 3, and 4, just giving them arbitrary names right now, and then later on we'll give them the Mulliken symbol rules once we figure out, what they are. So the first one is always a freebie, right? For every single character table, it's just a totally symmetric representation, so it's ones across the board. The next thing that I like to do is look at the um, another character table rule, which is that the sum of the squares of the dimensionalities, which is the character under the identity operation. In other words, sum of the squares of the dimensionality, we could write as 1 squared plus a squared plus b squared plus c squared, has to equal the order of the point group, which in this case is 12. And to remind you why that is, the order of the point group is the total number of symmetry operations in that point group. So one identity, four C3s, four C3 twice, and three C2s, so that equals 12. These dimensionalities, right, they tell you how many functions transform together in that space, and they're going to be 1, 2, 3, 4, 5. And most of the time they're going to be ones or twos. But in this case, actually, we're going to have three. We can walk through why, but basically they have to be 1, 2, 3s, 4s, or 5s. So let's think about this. It can't be 5, because if one of these values is 5, that's 5 squared is 25, that's already greater than 12. Can't be 4, because 4 squared is greater than 12, 16, right? It could be 3 squared. Now, one of them could be 3 squared because 1 squared plus 1 squared plus 1 squared plus 3 squared is equal to 12. So that looks like it works. It does work. Can it be anything else? Could it be 2 squared? Uh, well, 2 squared is 4. If we have two 2 squareds, that would get us to 8. And then if we had three 2 squareds, that gets us to 12. And then we have 13, so that doesn't work. If we have two 2 squareds, we get us a 2 squared plus 2 squared plus 1 squared plus 1 squared. That gets 10. So that doesn't work, too low. So yeah, it has to be this answer right here where we have 3 1s and 1 3. So that's a great rule to figure out your characters in this first column. And we're going to be using this to help us puzzle things out. All right, I'm just going to erase this so we have some more space. And so now what we're going to do is think about different functions. That's usually where we start off next in deriving the character tables. And we like to start with the linear function, so we start with the function x. And what we're asking here is now in T symmetry, does the x vector, right? So we'll draw a Cartesian coordinate system. This is the x-axis, the y-axis, and the z-axis. We're asking how does, actually, let's start off with z. Usually that's how we start off. How does the z vector transform with one operation in all of these classes? And so for the E operation, the only operation in the E class, Z goes to Z. That's the definition of identity. It takes everything to itself. That's not interesting. What about the C3 operation? Well, we saw from the previous video that one of these C3s, the easiest one to visualize is pointing up. And we're defining our z-axis as pointing up there. Let's do it that way. This is our principal rotation axis. Remember, our principal rotation axis always has to be in these character tables, how it's everybody does them and how it's defined in order for you to get the right answer. Your principal rotation axis has to be coincident with the z-axis. So this C3, one of the C3s at least, and all we have to do is one of the C3s, the C3 that we care about is coincident with the z-axis. So we're doing a 120-degree rotation and rotating this vector, but it's still pointing up when we do that. So z goes to z. Okay. If we do a C3 too, same idea. We do 240-degree rotation. That's the next class here, but z is going to go to z. Now, something interesting happens when we do a C2. And the C2 is definitely harder to visualize, but it's not really going, it's off axis here, right? And so when you have something that's totally off axis in x with respect to x, y, and z, that is going to get flipped, but it's going to get flipped 180 degrees, and it's going to go into some linear combination of x, y, and z. And so what that tells us is that z goes into, alpha x plus beta y plus um, gamma z, some linear combination. In other words, there's actually, these are x, y, and z are transforming together. That's what we figured out here. Okay. And so we actually have to think of a 3x3 matrix that explains this transformation correctly. And then the trace across this 3x3 matrix is going to be our answer for the character. That's a hard one to do. I do it in the TD character table derivation videos. And the answer ends up being -1. But you have to think about, okay, 109.4 degree angle of the tetrahedron that ends up, where does that come from? It's actually the arc cosine of 1/3, okay, gets you 109.47 degrees. And you do some trigonometry essentially from that, and you can get that. In this case, you can see my other video on that derivation, but in this case, we're actually not going to have to derive that. There'll be a trick where we won't have to do all that work because this character table is actually a lot smaller. And in some ways, because it's smaller, it's simpler than the TD. But you'll see in part 3 of this video series how in another way it's more complicated. But what this tells us at this point is that x, y, and z transform together. So when we go back to identity now, actually we have to hold x, y, and z together in a 3x3 matrix. But we know it's just the identity matrix that keeps those all together. That explains how x, y, and z go back to themselves. Then we take the trace of this matrix or the character of this matrix, and we use the symbol chi, right, to represent character or trace. That's why it's called the character table. And we get that the character for the identity operation is 1 plus 1 plus 1, which is equal to 3, which is why we have a 3 here. So that checks out. Now we can do the C3 operation. The C3 is going to be a lot easier to visualize than the C2 because the C3 operation is only moving things in the XY. When we think about this one C3 operation, that's coincident with the Z-axis. And so when we think about, all right, now how does that C3 rotate an X factor, for example? Well, it's going to rotate at 120 degrees out into a linear combination of X and Y. But we know we've done this sort of 2D rotation many times in these derivation videos. We know that we have to use the rotation matrix. And so what we're going to end up having now is a 3x3 matrix, but with a 2x2, with the 2x2 rotation matrix embedded in it. And we know what that is. That's just cosine of 2 pi over n. Here we're doing a Cn, C3, right, rotation. So we have cosine 2 pi over 3, sine 2 pi over 3. And I'm going to put the value 0 here because we're not doing any, this doesn't have any z component, right? It's not pointing, this vector isn't pointing up or pointing down. And then we have a negative sine 2 pi over 3. This is 2x2 rotation matrix, cosine 2 pi over 3. 0 again. And then we have 0, 0, and 1 for the z column because z goes to z. So then we take the trace of this 3 by 3 matrix, and the trace of that, sum across the main diagonals, is cosine 2 pi over 3 plus cosine 2 pi over 3 plus 1. Well, cosine 2 pi over 3, think about your unit circle, that's negative 1/2. So it ends up being negative 1/2 plus negative 1/2 plus 1, which equals 0. So now we figured out that the character under the 4C3 class is 0 for gamma 4. And then we do exact analogous thing for C3 twice, except now we're rotating by twice as much, right? And so this matrix becomes cosine 4 pi over 3 and cosine 4 pi over 3, and also the sign values becomes sine 4 pi over 3. This stays 1. I don't really care about the sign values because, again, the character table just takes the trace over this main diagonal. And so we can quickly write that the character, the chi, for the C3 twice operation is cosine 4 pi over 3 plus cosine 4 pi over 3 plus 1. Cosine 4 pi over 3 is also, to remember your unit circle, also negative 1/2. So you get negative 1/2 plus negative 1/2 plus 1 equals 0 again. So you get the same answer. So the character under the 4C3 twice is 0. Now we could do the visualization that I talked about that I did in the previous TD character table derivation video and figure out that this is equal to negative 1 through some quite difficult visualization and trigonometry. An easier way is at this point to just use the orthogonality principle. And so we know that gamma 1 must be orthogonal with gamma 4. That is that gamma 1, the dot product of gamma 1 and gamma 4 has to be equal to 0. That's one of our character table rules, that the great orthogonality theorem, all the vectors have to be orthogonal to one another, the irreducible representations. But remember that this is normalized to the number of symmetry operations in each class. And so what you end up having is a vector 1, 1, 1, that's the gamma 1, dotted with 3, comma 0, comma 0, comma x. We're trying to figure out what that value is, but then dotted by 1, comma 4, comma 4, comma 3. That's the number of symmetry operations in each class. We have to adjust for that. And that all is equal to 0. So of course, this term just goes away because we're multiplying everything by 1. We end up with something here. So we multiply that out and we get 3, but these terms are 0. 3 plus 0 times 4 plus 0 times 4 plus 3 times x equals 0. We end up with 3 plus 3x equals 0. And we solve for that, get x equals negative 1. And indeed, that's the answer that we got when we visualized this same sort of symmetry class in this operation for TD. Okay, point group, see the TD derivation videos. But anyway, this was a much quicker way. We could do this in this case because, hey, it was our last one we're trying to figure out. So we figure out that that's negative 1. Okay, so let's stop here for this one. And then we'll do the remaining 2 irreducible representations in the next video.